Inha University. So let me introduce the self-dual Chern-Simons-Higgs model mentioned by Professor Han a few minutes ago. And Chern-Simons theory, as you see, generally refers various field theoretic models which contains Chern-Simons term in their action densities. So this theory is used to describe many interesting phenomena in theoretical physics, such as the fractional quantum Hall effect, and in condensed matter physics, and the high temperature superconductivity, and so on. So there are many theoretical models in this theory, and the Chern-Simons-Higgs model is one of the simple models in the Chern-Simons theory, and it was proposed in 1990 by two independent research groups in order to explain high temperature superconductivity. For physical motivations, I would like to recommend these books, and Schaffenthaus, Gerald Dune, Isong Yang, and Gabriela Tanaka. Okay, let me skip some physical model and derivation of elliptic equation, and let me focus on the governing equation for the static finite energy solution of the Chern-Simons-Higgs model. I mean static, that the solution does not depend on a time variable, and it depends only on the spatial variable x1 and x2. So this equation is given on a two-dimensional domain, and lambda, u is a real-valued function, lambda is a positive parameter, and p1, pl are points in two-dimensional domain omega, and ma is the multiplicity of pa, and the domain, either the domain is a periodic domain or torus, or it equals our whole domain R2. Since we are looking for the finite energy condition, we require that the nonlinear term must belong to L1 space. So we must impose various boundary conditions on the solution U. So if omega is a torus, then we simply assume that U must be doubly periodic with respect to the domain, and U minus U0 must belong to H1 space. Here, U0 is some normalized green function, and in the case that omega is the whole domain R2, we have two possible boundary conditions, because this function is e to the u multiplied by e to the u minus 1. So we have two possible boundary conditions. The first one is called topological boundary condition. In this case, the solution is topological solution. This solution tends to 0 near infinity. The other one tends to minus infinity, as modulus of x tends to infinity. So and in this case, the solution structure for topological solution is rather simple. So at the end of my talk, I would like to mention briefly some existence results on non-topological solutions. Okay. The Chern-Simons-Higgs equation is often compared with analogous equations which arises in the abelian-Higgs model, which is an extension of the Ginzburg-Landau model. The governing equations for the static solution of abelian-Higgs model is given as follows. So this equation is used to describe superconductivity, and the order parameter, e to the u, is called the order parameter. It measures how deep the material is in the superconducting state at position x. So if e to the u is close to 1, then that point x is superconducting state. While if e to the u is very close to 0, then the point denotes the normal state. And moreover, this equation enjoys some uniqueness result, because as you see, the nonlinear term is just a linear function, and it is increasing with respect to the real valued function u. So for each value of lambda, positive value of lambda, this equation admits at most one solution. While the Chern-Simons equation, let's look at the nonlinear term. This, unlike the governing equations for the abelian Higgs model, the nonlinear term is a quadratic polynomial of its to u. It is not monotonic, so it is not linear. So this equation has a mathematically rich structure rather than this equation. In this case, it will turn out that this equation has at least two solutions. Okay, we can also impose some boundary conditions to get a finite energy condition. But in this case, we can impose doubly periodic conditions or topological boundary conditions when the domain is R2. But for this equation, this non-topological boundary condition is not possible, because in this case, this nonlinear term must belong to L1 space. So this boundary condition is not possible. Okay. Okay, let me mention some existence and asymptotic behavior for periodic solutions when the domain omega is a torus. If omega is a torus, this equality easily comes from integration by parts, and here capital N means the sum of multiplicities of each zero. Actually, this zero is often called the vortex point, and near this point, the material is approximately normal state. Okay. So, in view of this equality, we may raise two interesting questions. The first one is to prove existence of solutions. I mean, existence of solutions for various kind of two different kinds of solution. The first one tends to 0, and the second one tends to minus infinity as lambda tends to infinity. So, to solve existence problem for the solutions, we can use the method of super and sub-solution and the variational method and so on. Next one is to refine the estimates for the asymptotic behavior of solutions as lambda tends to 0. In this case, a very well-known method of uniform estimates and blow-up analysis for concentration phenomena can be used. So I think this is very interesting problem because asymptotic behavior, refined estimate for the asymptotic behavior may enable us to find various kinds of bubble solutions for the Chern-Simons-Higgs equation, which is not remain unsolved in many parts. So let me mention first the existence part. Okay, if we use the method of super and sub-solution method, we can get the existence of maximal solutions which satisfy some monotonicity. I mean, if lambda is sufficiently large, then the Chern-Simons-Higgs equation admits a continuous one-parameter family of maximal solution satisfying this monotonicity. Moreover, if lambda tends to infinity, then the maximal solution tends to 0 almost everywhere. Later, it was shown. This solution has important property that if U is any solution, U lambda is any solution, then U lambda must be strictly less than this solution. So in that sense, this solution found by super and sub-solution method is called maximal solutions. So later, uniqueness result for established for the maximal solution. I mean, if lambda is sufficiently large and there is a solution which is bounded below, then that solution must be equal to the maximal solution. This, okay. So if there are other solutions which are not maximal solutions, then those solutions are not bounded below. Okay, this is another approach to obtain existence result for periodic solutions. This is the usual variation approach. Okay, we introduce Green function to remove singularities contained in the Chern-Simons-Higgs equation, and we introduce some associated function I lambda defined on the subleft space H1. So by using this functional, we can obtain these results. If lambda is sufficiently large, here lambda 0 coincide equals this value, and this value are the same. So if lambda is sufficiently large, then this functional admits at least two critical points. One critical point is a local minimizer, V1, and the other saddle point. And the saddle point is obtained from the mountain path theorem. Okay, so we have at least two solutions. Later it was showed that V1 actually corresponds to the global minimizer. I mean, if lambda is sufficiently large, then the U0 plus V1 is exactly the maximal solution, and it is a global minimizer over L lambda. So, in view of the uniqueness result, we conclude that V1 is the unique global minimizer. L lambda has unique global minimizer, and V1 is the one. So this is another variational approach. So actually, the asymptotic behavior of periodic solutions as tends to 0 was initiated by Tarantello. In the paper, this theorem was presented. So after her work, people began to look for periodic solutions which satisfy some specific asymptotic behavior. So in that point of view, this approach is very useful to solve such a problem. So the main idea is this: if V belongs to H1 space, then we decompose V as W plus some real number. Here, the average value of W equals 0, and C satisfies these quadratic equations. Actually, these quadratic equations follows from this equality. Okay, this is an a priori estimate for the real number C. So we plug this function V into I lambda. Then we can rewrite this functional as these two functional. So if we find critical points of this functional, then we can find a periodic solution for the Chern-Simons-Higgs equation. So here you see that well-known Moser-Schrödinger functional is involved in this functional, and psi is given as follows, and B, the functional B, is defined as follows. So in this case, we have some ways to handle this Moser-Schrödinger functional, because we can apply the Moser-Schrödinger inequality and find a local minimizer or global minimizer for this functional. So in this approach, these authors produced some good existence result when the capital N is less than or equal to 2. Here the capital N is the sum of multiplicities. I mean, if there are at most 2 0 points, then they were able to obtain periodic solutions. In this case, if N is less than or equal to 2, then this Moser-Schrödinger functional is bounded below. So if we add some additional functional here, then this functional has global minimizer. So they, in such a method, they could obtain existence result. So now let me move to another topic, asymptotic behavior of solutions as lambda tends to 0. The first lemma is as follows. If lambda tends to 0, then the global minimizer or maximal solution corresponds to global minimizer of the function I lambda. It tends to 0 almost everywhere, but other solutions other than maximal solutions tends to minus infinity. So the saddle point obtained from the mountain path theorem also tends to minus infinity. So let me mention interesting thing. I mean, capital D. It's my mistake. In the second case, the Chern-Simons-Higgs equation is viewed as a formal perturbation of a Liouville type equation or mean field equation. If we consider this function, then the function W satisfies this equation. So if lambda is sufficiently large, this term may be very small and can be dropped out from the Chern-Simons-Higgs inequality, Chern-Simons equation. I'm sorry. So if this term vanishes, this equation is mean field equation. So this relation was intensively studied by Nolasco Tarantello, Ding, and other professors, Chen-Ning Wang, and so on. There are many literature in this topic. So concerning asymptotic behavior as lambda tends to 0, myself and Nam-Gon Kim were able to slightly improve this behavior. I mean, if lambda tends to 0, and if U lambda is a periodic solution, and if lambda tends to 0, then U lambda satisfy one of these alternatives. Actually, only maximal solutions satisfy this convergence. I mean, this convergence can be improved to this, and other solutions, including the saddle point, satisfy this alternative. So in the last case, we may improve this result. We have boundedness condition or concentration phenomenon. The solution, this function, if U lambda is a solution of the Chern-Simons-Higgs equation, then U lambda plus log lambda is either bounded locally in L infinite space, or it may show concentration phenomenon. I mean, there exists a non-empty finite set S such that U lambda tends to infinity uniformly, and on any compact subset of omega minus S, and the nonlinear term converges to the finite sum of Dirac masses. Here the mass is greater than or equal to A pi. So in this case, we call Q a blow-up point for U lambda, and S a blow-up set for U lambda. So actually this lemma follows from the concentration compactness principle for Liouville type equations. The concentration compactness principle for these equations were extensively studied by many authors from the 1990s. So two of these authors are sitting in this classroom. And okay. So as a corollary, we can obtain an interesting fact on the periodic solutions. Okay, we recall that we have found global minimizer and a saddle point of the functional I lambda. So global minimizer tends to 0, so we have nothing to do with we have nothing more to do. But so we focus on the saddle point obtained from the mountain path theorem. So as lambda tends to 0, what happens to the saddle point? Okay, if n equals 1, then the solution is bounded in some sense. I mean, the first case occurs if n equals 1. It is because this simple inequality. If blow-up occurs, then the number of blow-up points must be less than 1 over 2, which is impossible. So it is bounded. If n equals 2, this is the case n equals 2 is a delicate case. So in this case, the first case can occur or the second case can occur. So it depends on the location of 2 points. But if n is greater than or equal to 3, then the second case do occur. So in this case, there exists one point such that u lambda tends to minus infinity uniformly on any complex subset, and the nonlinear term tends to 4 pi n their Dirac mass at q. Here, q is a maximum point of the Green function. So, one of the interesting problems which remains unsolved is the existence of the third solution. We have already found 2 solutions. One is the global minimizer, and the other a saddle point. And the third solution, the existence of a third solution, is a very interesting problem. So, with the help of this lemma, so I was able to find the third solution. Okay, if n is not greater than 5, then we have third periodic solutions if lambda is sufficiently large. Concerning the asymptotic behavior of that solution, we have the following. If n equals 3, then u lambda plus log lambda is bounded locally in this space. But if n equals 4, I don't know. That is also a delicate case, so I don't have any conclusion on that. And however, if n is greater than or equal to 5, we have only partial existence result. There exists a sequence lambda n which tends to 0 such that the Chern-Simons-Higgs equation admits a solution un. And if lambda n tends to 0, then along a subsequence, and we may have 2 possible asymptotic behavior. In this case, we have a concentration phenomena for the solution, but there may be 2 blow-up points, 2 distinct blow-up points, and the blow-up points do not coincide with any singularities in the Chern-Simons-Higgs equation. And second possibility is that there is only one blow-up point. In this case, the blow-up point is the singularity. And here, the positive integer alpha is the multiplicity of q. So this theorem indicates that the existence of a third solution or fourth solution may depend on the number and the location of the singularities Pn blah 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 Pl. So if the number is getting larger and larger, and if the location of Pj are complicated, then we will get many periodic solutions. Okay, let me sketch the proof in brief. The proof is based on the variational approach, and we will use this functional. And this functional is defined here. Okay, in this case, the Moser-Schrödinger functional is contained in this functional. But okay, let me mention something about this functional. The function psi is defined only on this range, not on all R. So we must impose some constraints on the function space. I mean, this quantity must be less than or equal to 1. Okay. Okay. This is the constraint. But if we impose such a constraint, then the variational approach do not give us any remarkable result. So main idea for the proof is that we replace this function with a very good function f defined for all positive value of t. So we look for a critical point of this modified functional. Okay, this is f, which is defined for all t, positive t. So we may choose a functional f in such a way that the modified functional admits a global minimizer. But in this case, the global minimizer may coincide with the set point found from the mounting path theorem. And the set points satisfy this asymptotic behavior as lambda tends to 0. So instead, we look for a set point, W lambda, by using the minimax method, well-known minimax method. So in that case, we must choose some functional and suitable family H of functions. For this purpose, we will use the compactness of Moser-Schrödinger functional here. So for this purpose, we adopt the notion of the center of mass and improve the Moser-Schrödinger inequality. So let me treat this case only, and the other case is very similar. So in this case, we can choose some functional f and the family of functions. So in this case, we can conclude that this value is greater than or equal to this value. So this inequality follows from the improved Moser-Schrödinger inequality. And on the other hand, we can find a class H0 of test functions such that this inequality holds. So if we apply a well-known minimax method, we can find a function u lambda such that u lambda, which is a solution of this equation. Here, mu lambda, we see mu lambda instead of lambda. If this is the number of lambda, then we have the third solution for all values of, or for possible values of lambda. But because we used the modified functional, instead of the original functional, so we have mu lambda instead of lambda. But if n is not greater than 5, and lambda, if lambda is sufficiently large, then mu lambda equals lambda. So in this case, if it, some normalized function of u lambda satisfy this this equality. So if we compare this result and this result is satisfied by a set point. So we see that the solution we found is different from the set point which was obtained from the mounting path theorem. So we have the third solution, and the asymptotic behavior for u lambda follows from the compactness, concentration compactness lemma proved by myself and Nam Kim. And this is a very interesting open problem. The remaining open problem is existence of various periodic solutions satisfying specific behavior. So very recently, Professor Chang-Sho said that he had constructed various blow-up solutions under some non-degeneracy conditions for the blow-up point. So, so that would be a very interesting problem, and I hope there more and more solutions can be found by his method. Okay. Finally, I would like to mention some existence results for planar non-topological solutions when the domain is a whole domain R2. So in this case, the solution, we impose non-topological boundary conditions on U, and elliptic estimates show that U behaves like a logarithmic function near infinity. So we have the same equation, but we have a little different boundary condition near infinity. And in this case, the corresponding energy is equal to 2 pi multiplied by beta plus 2n. N is still the sum of multiplicities. Here are some existence results regarding non-topological solutions. In this literature, the existence of radial solutions were presented. The Chern-Simons-Higgs equation has radially symmetric non-topological solution if beta is strictly greater than 2m plus 4. In this case, all the singular points equals 0. And in the general situation, when these points are not necessarily the origin, then existence results was presented by Choe and Inha Uni below. In this case, beta is still greater than 2m plus 4, but beta must be very close to 2m plus 4. This is maybe the first result on the general situation. And the other interesting result was presented by Professor Lim. And in this case, he assumes that each multiplicity is 1 equals 1, and the location of vortex point, the location of PA satisfies some symmetric conditions. And he also assumed that lambda is sufficiently large and beta must be greater than 6n. Then he showed that there exists a family of solutions such that the nonlinear term show concentration phenomena near each singularities as lambda tends to infinity. So at this moment, the existence of non-topological solutions for every possible values of lambda and every possible values of beta is still open. I hear that Professor Kwangseok Choe has an idea on this equation. But anyway, I would like to mention some partial existence result, which is a joint work with Nam-Gon Kim. And this theorem states that, Pj are arbitrarily given, and this theorem states that for some values of lambda and for some values of beta, the Chern-Simons-Higgs equation admits a non-topological solution. So in order to prove this theorem, we adopt the same method which is used in the proof of this theorem. The proof is parallel to the proof of theorem 3. But in this case, unlike the periodic case, the functional is not bounded below. I mean, the infimum of functional v is 0. So we cannot expect global minimizer of any modified functional. But in this case, we can find minimax value, and we can find the saddle points of some modified functional. So we have non-topological solutions in very restricted situation. Okay, this is end my talk, and thank you very much for listening.